I'd like to invite our next speaker, Dana Alsulaiman. And Dana is from the Division of Physical Science and Engineering at the King Abdullah University of Science and Technology in Saudi Arabia, a very inspiring emerging researcher. She's going to talk about the next generation of electrochemical biosensors for microRNA detection based on rational design of peptide nucleic acid functionalized 2D nanomaterials. Dana, if I can invite you to the stage.
Is it on? There we go. Thank you so much, Veena, for that introduction. And thank you to the entire IWAM team for having me and for hosting such an amazing workshop. Thank you to, obviously, Professor Tony Teaton for inviting me to come here. So it's truly an honor. I've been meeting a lot of people that I idolize here almost every day, so it's great. So today, I'm going to talk about or introduce you to a versatile toolbox that we've developed in order to enable us to take 2D nanomaterials and turn them into advanced biosensing platforms. So just a little introduction to myself so you understand my background. I'm currently an assistant professor at KAUST. I just started 2 years ago, my lab, and we work at the interface between material science and bioengineering. Prior to going there, I did a quick postdoc at MIT in the chemical engineering program, and I did my undergrad master's and PhD in bioengineering at Imperial. And I've developed these different skill sets in very interdisciplinary fields that I believe can be really honed in to tackle some important healthcare problems that we're facing. Over the years, some of this research has gained some exciting awards over time, and one of the ones that I'm really excited about and proud of is the L'Oreal UNESCO for Women in Science Award, just recently in 2023. So I'm quite proud of that one. Let's get into the science. So what really motivates our research? We're driven by the burden of existing healthcare approaches and healthcare strategies, but we're really excited about the promise of precision medicine or personalized medicine approaches. So what do I mean by traditional approaches? Let's say we're trying to detect cancer. What typically happens is, firstly, patients have to present clinical symptoms, right? So maybe pain or other types of clinical symptoms. That's already at the later stages of the disease. Then you typically have to undergo some imaging modalities, CT scans, maybe MRIs. And finally, the patient has to undergo some invasive tissue biopsy to confirm the presence of this neoplasm, right? So we can clearly see the disadvantages of existing approaches. Now, there's this push to move towards much more patient-centric precision medicine approaches, where essentially you're taking a biofluid sample from each patient, and then you're detecting from it a set of biomarkers on these advanced microtechnologies or biosensing tools. And these biomarkers or biosignals can be from different classes or worlds. It can be proteins, they can be DNA, RNA, metabolites, and so on. And the idea is to analyze the levels of these biomarkers and then use that information to inform clinical decisions, whether that's early diagnosis of a disease or even choosing the most effective therapy for that patient. And so what we're trying to do in the lab is trying to accelerate this paradigm shift from traditional to precision medicine. And I'll show you how we do that with our technologies. Now, I mentioned that there are many different biomarkers of disease. They come in different flavors. And the one that I'm particularly interested in that's quite promising as a liquid biopsy biomarker is called microRNA. So a little bit of a introduction to it. You'll see it's right there in red. It's a short, non-coding RNA, so it doesn't encode for proteins. However, it plays a very important gene regulatory roles. And what's exciting about microRNA is that they actually end up in all biological fluids. They get packaged into extracellular vesicles, proteins, and so on, and end up in the bloodstream. And from there, they end up in all biofluids, urine, serum, saliva, and even interstitial fluid under the skin. So this means that we can sample them in a minimally invasive way. Wonderful. So when you start looking at patients and the levels of biomarkers in patients, particularly age-related diseases, whether that's cancer or neurodegenerative disease, you'll see that the there's a big dysregulation in the levels of microRNA. So microRNA get either overexpressed or underexpressed in the patient or even in the tumor tissue when compared to normal tissue. So you'll see here a heat map showing a whole panel of microRNA listed on the right, and you'll see that red shows this overexpression when compared in the tumor when compared to the normal tissue. And this is basically a signature of gastric cancer. Right? And another type of cancer, colorectal or breast cancer, would have a completely different dysregulation profile. So if I can develop a technology that can detect, or through multiplex detection of microRNA, that I can answer many clinical questions, including what is the disease that the patient has, what is the type of the disease, and you can even inform therapeutics as well. So why aren't we currently using microRNA in the clinic? Well, they're very difficult to detect because they're very low circulating concentrations. So we're talking picomolar to femtomolar levels, roughly, in the blood. They're also very short in length, so PCR isn't really designed to detect that, and you require additional steps. There is very high sequence homology among family members. So in a family of microRNA, from one to another, there's only a single it can be as low as a single nucleotide that's different. And finally, the traditional existing approaches, you all know that. It's the same approach that we use to detect viral RNA for COVID, is based on PCR or other techniques that are quite complex and time-intensive and costly. So what is our vision? Well, really our vision is to enable this next generation biosensors and actually turn advanced 2D materials into biosensing tools. And this is our ultimate goal here, which is probably very similar. You might recall like a glucose monitoring device. And instead of detecting glucose, we would be detecting a whole set or panel of microRNA on this miniaturized biosensing surface. So where does materials come into play? And all of the kind of engineering and design comes really just at that miniaturized biosensing surface. So if you zoom in on that, there are various components that come together that enable you to transduce biorecognition events, so the detection of the biomarker, into analytical signals that we can analyze. And that interface is really where the fun materials comes into play. So where do we really need advancements in materials and biosensing? Number one, we need to think about what is our bioreceptor. What is that molecule that is going to bind specifically to my target? That could be an antibody, and in this case, I'm going to talk about a really interesting bioreceptor called PNA. Then, of course, you need to think about what is my transducing material? What's my transducer? And then you need to think about, well, how am I going to connect these two with each other? What is my biofunctionalization? What chemistries am I going to use? And finally, once you put that biological fluid onto that sensor, is it going to be stable or is it going to foul? And can I develop materials approaches or even modifications to my surfaces to prevent this biofouling? So that's what I'm going to talk about. Let's start off with the bioreceptor. This is really the heart of my lab. So all of the different biosensors we develop are really kind of focused around this bioreceptor. So when you try to detect nucleic acids, typically what people would use is just another nucleic acid that's complementary, right, in terms of its sequence. So primers, short strands of DNA, they're complementary to your gene of interest and so on. So instead of that, we use synthetic mimics of DNA. So if we look at a DNA right there, you'll know that the backbone is a sugar phosphate backbone, right? And then you have your recognition units, your kind of ATCGs. But if you replace that sugar phosphate backbone with a pseudopeptide backbone, you can also make your own kind of synthetic version or pseudo-mimic of DNA or natural nucleic acids called a peptide nucleic acid. And why would you ever want to do that? Well, the main thing that you notice here is you got rid of that negative charge. So you got rid of that electrostatic repulsion that happens between two strands of DNA. You no longer have that. What that means is that you have much higher thermal stability between a PNA and a DNA versus DNA-DNA. The duplex is actually stable under extreme conditions of pH and temperature. With that, you also get higher sequence specificity. So if there's a single nucleotide that is non-complementary, so mutation, the PNA will not bind at all. And finally, because it's not really natural, your enzymes in your body, your proteases, DNases, RNases, are not able to recognize this. So it's very stable. And what I think is one of the most important things is that you can actually print out this material in the lab by hijacking very advanced solid phase peptide synthesis approaches that have been used for years to synthesize peptides, because it's just got the same backbone. So that's what makes it really cool. Well, what can we do with this PNA? Can we play around with it? What can we use it for? And so, of course, with the PNA, you can play around with the sequence. You can choose whatever sequence you want to target, whether it's microRNA or a viral RNA. And then you can also add anchoring functionalities to enable it to then bind to your platform. Maybe it could be a lateral flow assay on paper. You can put it within hydrogels. You can put it on 2D materials, which is what I'm going to talk about today, on glass, and of course on electrodes for electrochemical sensing. You can also change another thing, well, you can add some application-specific moieties, such that upon binding of the PNA to the target, you get a signal that results in electrical or electrochemical readout. You can get some optical or fluorescence-based readouts, and you can also modify the PNA in interesting ways to make sure that you can deliver it into cells for some therapeutic applications. Right, so with this PNA, let's talk about the synthesis of this PNA. We've actually established, to our knowledge, the first kind of full peptide and peptide synthesis, peptide nucleic acid synthesis workflow. So how would you go about synthesizing it? I used to do this manually in my PhD, but I managed to get myself a nice automated peptide synthesizer. So this is a peptide synthesizer. You've got all those ports for amino acids. So instead of the amino acid, you can plug in your monomer unit for PNA, and that's how you can synthesize this peptide nucleic acid. So after you synthesize it, you want to purify it. You can then validate it with mass spec, and finally you can freeze dry it, have it in powder form, and you can give it to your collaborators. You can use it in the lab for various projects. Just a brief intro to solid phase peptide synthesis, because it's really what drives us. It's a very simple approach where basically you can grow chains, right? You can grow a chain of amino acids, or in this case, a chain of peptide nucleic acids on a solid support, on a resin. And it involves repeating these 3 steps over and over again every time you add a monomer. It's very simple. You activate the monomer, you do the coupling, so peptide-based chemistry, and then you deprotect this big green bulky group, which deprotects and enables you to react to the amine with the next monomer. And you repeat this over and over again. So with this PNA, what can we do? We can do a whole spectrum of PNA-based biosensors. And these are some of the PhD students and postdocs in my lab working on different biosensors that are truly enabled by this PNA. And you can play around with the transduction. So Ghanima, she does a resonator-based biosensor where binding causes shifts in frequency. Haliang does some optical hydrogel encoded hydrogel particles that light up. Duro does some nanopore-based readouts. So you get binding, but then you pass the DNA through a nanopore, and you're able to detect markers there. Of course, today I'm going to talk about electrochemical biosensors, and you can even do some nice microneedle patches that you can apply onto the skin and detect microRNA that's present in your interstitial fluid. So today I'm just going to talk about some of our work with electrochemical biosensors. And why am I focusing on that? Well, I think a lot of you are very well aware of electrochemistry and its merits, but when it comes to biosensing, we're really interested in it because it really gives you a quantitative signal. It allows you to look at a massive or very large dynamic range when compared to, let's say, colorimetric readouts, and it's really amenable with point-of-care testing. So how can I prove that? Well, this is the most commonly used biosensor in the real world. That's a glucose monitoring device. And if you just focus on that region there, you have a basically printed electrode. And the principle is exactly the same as this 3-electrode electrochemical cell. You've got a working electrode shown in gold, you have a reference, and you have a counter. And the idea of electrochemical biosensing is typically you would functionalize your working electrode with that bioreceptor antibody, or in our case, the PNA. You apply a potential bias between the working and the reference electrode, and you complete the circuit with the counter. And typically what people do is different kind of photometric or amperometric techniques in order to investigate and understand redox reactions that are happening at the surface of your electrode. So one very common one is a CV, a cyclic voltammetry, and you sweep the voltage and then look at oxidation and reduction currents. And really you're answering what's really happening, what are the electron transfer processes that are happening at the surface, which is wonderful because then I can use this principle to monitor any binding events happening at the surface. So this is the most simple kind of demonstration of a biosensor, or electrochemical biosensor. You typically have your probe there on the surface, and then you're monitoring kind of the oxidation or reduction of redox active moieties. But then when a binding event happens, what happens is you typically block those molecules from coming to the surface, and you get a reduction in your current. That's kind of the simplest idea of an electrochemical biosensor. So we'll see how we've exploited that. So we talked about the electrochemical or the transduction mechanism. We talked about the bioreceptor. Let's now talk about what is our transducing material. This is where it gets a little interesting. So in this case, we've chosen to use 2D nanomaterials and actually change them or use them in the form where they form 3D porous structures or architectures, which is really cool. And I'll introduce you to two emerging materials that we've used in this way. So we've got not graphene, but laser-induced graphene, and we also use MXenes. So I'll introduce you to either of them. So has anybody heard of LIG before? Just a show of hands. Laser-induced graphene? And it was actually developed in Rice University, but it's similar to MIT. Has anybody heard of MXenes before? Oh, cool. Okay, so I'll spend more time on LIG. So LIG is really cool. It's not actually, you'll see from this SEM image right here, it's a 3D porous form of graphene. You can see here it's not as nice and 2D as we imagine thin sheets. It's this 3D porous form of it. And what's most interesting about it is how you make it. It's very, very simple to make. What you do is use, let's say, a carbon dioxide laser, and you shine it and irradiate it on a carbonaceous precursor. Typically, people would use polyimide film, but some more recent research articles on sustainable approaches have used like wood and other natural materials. And what happens is that you photothermally convert the sp3 carbons into sp2 carbons, rearrange the atoms, and you get some graphene or graphitic-like materials. Wonderful. This is a really cool material to use. It obviously has the other properties of graphene, including conductivity and so on. So the other, let's say, class or family of 2D materials that we've been interested in working with is MXene. And for the people that haven't heard of it, they're emerging class of 2D transition metal carbides, nitrides, or sometimes carbonitrides. And it has this formula Mn+1, XnTx, where M is the transition metal. And in this case, I'm showing you titanium. X is either carbon or nitrogen, and T represents the surface terminal groups that kind of coat the surface. And you can see right here, you have a lot of hydroxyl functional groups on the surfaces. We obtain them from our collaborator in my department, Professor Hossam Sharif's, and he gives us these Ti3C2 TX MXenes. We obviously have all the amazing properties also of 2D materials like high electrical conductivity that comes from the transition metal. But the most interesting kind of contrast when it comes to graphene is the fact that you have this sea of surface terminal groups, of these functional groups that I can now react or, let's say, functionalize with my bioreceptor. And because of this sea of hydroxides and oxides and even fluorines and chlorines, I also get some hydrophilicity there. So it's really nicely dispersed in aqueous medium. So this is the two different classes of materials. And really what got us interested is look at these two materials. They're really useful when it comes to this high surface area to volume ratio. We have 2D materials that form this 3D porous, extremely high surface area to volume ratio architecture. Why don't we use this for extremely efficient transducers and electrochemical biosensing? Not only promoting, charge transfer, but also by allowing us to have a much higher loading of our bioreceptor molecule. And that means, or translates to, in electrochemical biosensing, so much higher sensitivity. So we've also obviously looked into literature to see, well, have people done this? Well, yes, some people are also thinking about this. And if you look up, obviously, the word MaxScene, you'll see there's this exponential increase in the publications of MaxScene since the discovery in 2011. But if you look at MaxScene and Biosensor, you see there's this really little exponential also increase in the use of kind of MaxScene in biosensing. It's a much younger field, but it's clearly a very interesting field, and people are looking into that. And if you do the same with LID, you'll see a very similar trend. These are new fields, but they're particularly emerging and interesting. And if you look into the literature and see, well, what have people done? Typically, what people have done to turn these materials into biosensors is that they've combined them and created some nanocomposites. So in this case, they mixed MaxScene and graphene. They also wanted to detect glucose. And to achieve enough sensitivity, they've also had to use enzymes like glucose oxidase, which is something that we try to avoid when we're moving forward to the next generation biosensors for stability purposes and robustness. The other reason why people typically combine MaxScene with another nanomaterial is to prevent the restacking of MaxScenes, and that's something that we're also going to address. Another example here is that I think they're detecting some nucleic acids, and they also had to involve some signal amplification approaches in order to achieve the sufficient sensitivity, and they've had to use enzymes there as well. So really, we wanted to understand, well, what are the limitations and how can we address them? And the main ones is the fact that it's quite complex. You need to incorporate multiple nanomaterials for stability purposes and for biofunctionalization purposes, which is typically physical, kind of physical interactions rather than covalent bonding. And finally, you need to use enzymes, or at least the literature requires the use of enzymes, which limits the robustness and specificity. So what is our approach? We decided that we're going to actually take our 2D nanomaterials and covalently, or in some cases even very strongly or efficiently, functionalize them with our robust bioreceptors, our PNA probes. And so using our toolbox, what you can do is you can either click it or you can stack it. So you can take your nanomaterial and click it on with your PNA probe. As in this case, we have a clickable probe that's been stuck onto the MaxScene surface covalently. Or you can develop a pi stackable PNA probe and stack it onto your graphene. And with that, we were hoping that we should be able to get a much higher probe loading, improving sensitivity, and also maintaining the high electrochemical properties and the stability of the entire system. So I'll talk about each one individually. So we'll start with the first one, which is the PNA-clicked MaxScene. And essentially what we did is we took these MaxScene nanosheets and we clicked on, using click chemistry, our PNA probes, and we deposited these MaxScene sheets onto a glassy carbon electrode. And when we did that, we actually formed a 3D porous PNA MaxScene type of architecture there that has a massive surface area to volume ratio. And because of this, we were able to achieve a completely sensitive, or robust, sensitive, completely enzyme-free electrochemical detection of microRNA that rivals the sensitivities of existing approaches. So how does it work? Well, you start with your MaxScene nanosheets that have the PNA probes, and you add your biofluid sample. You get hybridization happening with the target microRNA. Then you remove any non-specifically bound molecules. We then add a redox label. And then finally, we can detect it using electrochemical sensing approaches. And really, the current there is directly correlated with the amount of microRNA that is bound. So to start ourselves off, we started with a synthesis. Oh, it doesn't look very nice. But we started with synthesis of a 7-mer, very short 7-mer clickable PNA that is complementary to microRNA number 141. It is specific to prostate cancer and colorectal cancer. And you'll see here we've got 7 mers. We've got some positively charged amino acids there at the end for solubility purposes. And then you have this DBCL moiety that I'm going to talk about that gives it its clickable nature. And for chemistry, we wanted to make sure that our chemistry or our biofunctionalization is completely bioorthogonal. And so we were inspired, obviously, by the 2022 Click Chemistry, particularly by the work of Caroline Bertozzi, where we wanted to use copper-free Click. And so what we did is we take our maxine, which has the hydroxyl functional groups, and we wanted to introduce some azides, azidos, on the surface. So very simply, we did some silanization with an azidosilane. And now we have the azide functional group. So you can do copper click, but we wanted to do the copper-free click. And to do copper-free click and eliminate the copper catalyst, all you need to do is basically, why we got the Nobel Prize, is use a strain-promoted azide alkyne cycloaddition reaction. So you can get these DBCO moieties, you functionalize them on the PNA, and then you can click this DBCO PNA, dibenzocyclooctane, and you can do that completely at room temperature without the use of click. And you get this very nice bioorthogonal click happening. Now, this schematic is extremely simplified. You don't have one PNA sticking out, a massive PNA on each maxine nanosheet. What you get is you get a sea of PNAs on the top of maxine, but also on top and on the bottom of every sheet, right? And this entire reaction is obviously happening in solution systems. What happens with pristine maxine is if you keep this suspension at room temperature for a very long period of time, you get these sedimentation happening. But after our functionalization, we get this really, really nice PNA maxine nanosheets floating. You keep it at room temperature for however long, it still maintains this really nice colloidal dispersive solution. Then we started off with our materials characterization. First thing we did, very simple, let's have a look at the zeta potential and the surface charge. And the bare maxine gives us a very nice minus 30 or so millivolts. And this is obviously because of the massive hydroxyl groups on the surface. You've got a lot of fluorines and chlorines. Then after we silanize it, it shifts to minus 18, goes slightly more positive, which is a very good indication for us that, look, we've got some of those hydroxyl groups that have reacted. But really, is it the correct chemistry? Did we get the silanization happening? We had to look at some XPS. So if you look at the survey spectrum of XPS here, we have our bare maxine shown in red. You see the titanium, you see the carbon. And then if you silanize it, shown in black, you see very nicely the appearance of the silicon peaks. Right there. You also see a nitrogen peak binding energy there around 400. And when you do the click chemistry with the PNA, what you notice very nicely is the increase in the intensity of the nitrogen. You also get an increase in the intensity of the carbon there. But let's zoom in a little bit more and do some high resolution. We did that. We had a look at the carbon and the titanium. We know that there's some really nice carbon-titanium bonds with the bare maxine and so on. Then the next step is the silanization. So we looked into the details of high-resolution N1S spectra. For the precursor, there is azidosilane shown there. And you see here in the nitrogen binding energies, you see 3 species very nicely associated with the azido functional group. Then after silanizing the maxine, you see exactly the same binding energies, indicating that we've got that azido group on the surface of our maxine. Wonderful. So the next step is the PNA click. So we also did high-resolution XPS for the PNA by itself. And you see very nicely the binding energies in the N1S, and you see exactly the same ones present after clicking with the PNA. Wonderful. So we've got proof, materials characterization proof that we've got the material that we've intended to make. Let's have a look at some electrochemical characterization. So those sheets that are functionalized, we just drop cast them onto the surfaces of our glassy carbon electrode and then study charge transfer, the resistance to charge transfer using electrochemical impedance spectroscopy. This is a really great technique to use to study charge transfer resistance. And so we obviously start off with just looking at the glassy carbon charge transfer resistance. And the bare glassy carbon electrode has a charge transfer resistance. This is indicated by the radius of the semicircle. It gives you information about charge transfer resistance. So it's about 1.8 kilo ohms. So once you put the bare maxine on the surfaces of GCE, what happens is this massive reduction in the charge transfer resistance. It tells us that, yes, we have this really nice enhancement of charge transfer that's happening due to these maxine nanosheets and high surface area to volume ratio on the surface. So now let's take some of our PNA functionalized vaccine and put it onto the surface, and you get this increase again in the charge transfer resistance, meaning that we've got something blocking electron transport that should be our PNA probe. And to confirm that it's our PNA probe, not just something else on the surface blocking charge transfer, we then added our microRNA. We allowed the microRNA to hybridize. We washed off anything non-specific. Then we took another EIS. And you see very nicely that there's a further increase in charge transfer resistance, meaning that you've got that bulky double strand happening at the surface. This is great, but it's a turn-off signal, right? So for me, you typically want to have turn-on signals. Why? Because turn-off signal means binding results in a decrease in my current, right? And this decrease in current can also happen due to other things, like, let's say, fouling of the surface by proteins, non-specifically. So I want a turn-on signal. And one approach for people, typically in electrochemistry, to do turn-on is they add a redox active intercalator. One very common one is methylene blue. And so that's what we did. And we did some control studies just to confirm that we have this nice turn-on signal. So we had the duplex forming. We added methylene blue. It intercalated between the double strands. We washed off anything non-specifically bound, and then we take a reading. And the control or negative control to that is we did not add any microRNA. We added the methylene blue, allowed it to incubate and intercalate if it wants to. It's not going to. And then we wash off, and then we take a reading. Now, normally, just before I show you the result, normally, this strand right there is a negatively charged, also single-stranded DNA or RNA. So you typically do get a little bit of electrostatic interactions between the positively charged methylene blue and the probe. In our case, we don't have that, and that's exactly what we observed. Basically, no oxidation peak current happening in the negative control, which is really, really cool. It's a given, but it's really cool to see that essentially you have no noise there, no non-specific interaction. So you get a very nice oxidation peak current in the presence of your microRNA. Great, so we formed our turn-on signal right now. This is just to show you the reaction that's happening on the surface. Very, very simple, just methylene blue that's being oxidized and reduced. Nothing to do with the nucleic acids, but it's there because the duplex is there, and the duplex is there because of specific interactions. Great, so everything that I've been talking about right now is with that 7-mer PNA. And of course, what we wanted to do is after we got that signal, we want to make sure to increase this analytical signal as much as possible to help our specificity, to improve our sensitivity. And so what we did is, knowing that our 7-mer PNA only occupies about, less than half or even a third of our microRNA, which is about 22 nucleotides in length, we said, well, why don't we just make a much longer PNA? It's not as easy as it sounds. Making longer PNA obviously gets you slightly less yield and synthesis, but we made a much longer PNA that's complementary to the target, and we said that, assuming we've got about 1 methylene blue per every 2.5 base pairs, we should get double the amount of methylene blue, right, at the surface. And if everything is working exactly as we expect, then we should also get doubling of our sensitivity. And that's what we made, the 17-mer. It's exactly the same, except for the fact that it's longer. And we did a calibration curve. So what you do with the calibration curve is you add microRNA at increasing concentrations from 0.1 femtomolar up to 1 nanomolar. And the red curve shows you the calibration in the 7-mer. And then the black curve shows you the calibration curve when we had the 17-mer. So we actually observed almost doubling of the sensitivity of our sensor and a reduction in the limit of detection by 56%, which is great. So we're now approaching and even exceeding the sensitivities required for endogenous microRNA detection. So I've shown you CVs, but another method that you can use to look at oxidation and reduction at the surfaces is differential pulse photometry. This is a bit of a more sensitive technique because you essentially eliminate any capacitive currents and you're just looking at the Faradaic. And this is what we did here. So we did a calibration curve using DPV, and we plotted that, and we managed to get a very nice limited detection of 40 attomolar. So 10 to the minus 18, so much, much more than you actually need for endogenous microRNA detection. So great, we've achieved kind of sensitivities that can rival PCR in a fraction of the time and a fraction of the cost, happening in 30 minutes. But that's not all you need for a biosensor. Is this signal specific to that microRNA? And if I change the microRNA sequence by 1 nucleotide, do I still get the signal, or am I able to eliminate it? So then we designed microRNAs with some mutations. So if the green one shows you the target microRNA 141 that's specific to prostate cancer, we then designed some with single nucleotide polymorphisms, or SNPs, or mutations, shown in red. And we designed them to actually be not in the middle of that sequence, actually at the end, to really make sure and to challenge ourselves and to make sure that, is this binding happening or not? So we have that A there, and we have a 2-SNP situation with an A and a U that are mutated, and a 3-SNP situation. And we got some really exciting results. So if we normalize the target to 100%, even with a single SNP that's at the end, not in the middle. So by the way, the location of where this mutation is affects the stability of this duplex. And typically, if it's in the middle, it's destabilizing. And if it's at the end, it's not as. So even with a single SNP, we get almost a 75% reduction. And with 3 SNPs, there's basically no binding happening, which is really great, particularly for microRNA sensing. So that was the first platform that used some 2D materials. And we did a very, very similar approach with the LIG-based biosensor, but now you're working with a slightly different chemistry and a different material. So instead of a click group at the end, we actually added a pi-pi stackable group. Particularly, we used pyrene in order to stack our PNA directly onto the LIG. So we've printed directly our electrode. No need for a glassy carbon that's coated with something else. Directly, you can print out your electrode that also acts as the transducing material that's extremely porous and 3D. Then you do a single-step functionalization, literally incubating it with the stackable PNA that we've made. And then you can use it in the electrochemical sensing, very similar approach to before. And to cut the story short, we did very similar materials characterization, and we did some electrochemical characterization, also managed to achieve a very high limit of detection, even sub-attomolar levels. So to summarize these two approaches, one more thing that's really exciting about this one is because you print it in a screen, or fabricated in a screen-printed format, you can actually directly plug it into these miniaturized potentiostats that are commercial, plug it into your phone, and do real-time detection on a phone without any massive instrumentation or equipment, directly on the phone itself. So this means it's truly amenable with point of care when compared to the previous platform. So to summarize these two platforms, where are we at right now? Great, we've managed to achieve the sensitivities we require, really large, over 6 orders of magnitude dynamic range, without needing to thermally cycle as you would in PCR, and all of this within 30 minutes. But of course, there are challenges. So what I've been showing you is microRNA that's been floating in really pure, nice buffer solutions, right? That's obviously not the case in real life. You're going to have serum or even more complex blood, right, is where the microRNA is going to be in. So we started to do some of those experiments. What would happen if I'm trying to detect microRNA from serum? And what happens is at different concentrations, you'll see there, roughly the same trend, is a 30% reduction in the analytical signal. So that's a 30% reduction in our sensitivity. So this is a challenge that we're trying to address right now. And why do we get that? Obviously, because of the challenges of surface biofouling. You've got some other proteins and molecules and sticky things in your biological fluids that can stick to the surface and foul it. And we're currently developing materials or material coatings that enable us to form an anti-fouling surface on our 2D nanomaterials. The other thing is very important, which I mentioned at the beginning, is I'm just detecting 1 microRNA, which gives me nothing, in terms of clinical pathological information. You cannot base your clinical decision on 1 biomarker. You, in fact, need an entire panel. So maybe some of you have seen this curve before. It's called an ROC curve, and essentially gives you information about the clinical accuracy of your test. So if you lie somewhere on this middle line, your test is a coin toss. Does this person have cancer or not? Let's flip a coin. It'll probably do even better than your sensor, right? It's a 50-50 chance. If you have, let's say, the Pap test, this is for cervical cancer, by the way. If you do a pap test, which is currently what's used to detect or at least screen for cervical cancer, you see that here in orange. It's not too bad. You're approaching the top left corner, which indicates kind of high sensitivity and specificity. It's not too bad. And if you use 1 microRNA, let's say shown in green or in blue, not too bad either. But the best performance happens when you have a combination, at least in this case, of 3 microRNA that you're detecting. And this is where you get the best sensitivity and specificity. So low false positive rates, and so on. What does this mean? In traditional biosensing, it means that, well, I need 3 sensors. Each one detects one different thing, microRNA 1, microRNA 2, microRNA 3, which costs money, time, but also a lot of biological fluid samples are being used. And obviously, we've talked about this before, but in the case of biosensing, there's this push towards multiplex biosensors. It's one device, but can detect multiple, and that's what we're currently working on right now. How much time do I have? Because that's it. So I'm going to skip through this and say thank you. Whoop. Go back. Go ahead. Just say thank you to everyone. There you go. Thank you to all of my team, obviously. This is my team and my collaborators and some of my mentors, and thank you all for listening. Thank you, Nina. Thank you.
Really fantastic talk, Dana. Very inspiring. Are there any questions for Dana? Andrew.
Hi, Andrew.
Thank you. I'm losing my hearing. Thank you very much, Dan.
Thank you, Andrew.
Can I just understand, I think I understand that you screen print the polyimide and then laser irradiate to get the LIG. Is that right?
You actually start with a polyimide film, and then you heat it with a laser. And where the laser hits, you form the graphene or the porous graphene.
So you
exactly.
create it by actually addressing it with the laser.
Exactly.
What about the MaxScene? How do you deal with the matrix there? Yeah, it's a emulsion suspension in solution.
Yes, that's right.
What do you do next?
That's right. So after we functionalize it in solution, so the sheets are functionalized on top and bottom and everywhere with the PNA, all we do is we drop cast it onto an electrode surface, and we dry it.
Right.
And that's how we get the kind of 3D porous MaxScene. Yeah.
Thank you for explaining.
No worries. Thank you very much.
Thank you. One more question. Divya?
Thank you.
I have a very quick question.
Yes.
During the co-detection of mRNA, how are you so sure that this is the one which you are detecting?
Yeah, so what I've shown right now is just a single-plex biosensor. We have not demonstrated or done any multiplex detection of microRNA. There are many different approaches that you can take with that. One approach, for example, is to, let's say, choose a different redox active molecule that has a slightly different oxidation peak potential. That's one approach. And the other approach that at least we were showing is to have multiple different electrodes, miniaturized electrodes that are very close to each other, and each electrode is functionalized specifically with a different PNA. And so you know that the signal that's coming from this working electrode is obviously associated with the first microRNA, and so on and so forth. So it's kind of miniaturized, not purely multiplex, but close enough, at least with electrochemical sensing.
Okay, because in the CV analysis, we can have different type of current responses.
Yes.
So if the concentration differs for the mRNA also, the current may be same for different species. So then too we can't detect whether we are getting the peak current from different species.
That's right. So the redox active molecule that's generating the analytical signal is always exactly the same. That's the methylene blue. So it'll always give us exactly the same. And the specificity to the target comes from the PNA. So if I design the PNA on different ones, then I know which one comes from which microRNA. Thank you very much for that question.
Okay, well, if there are no further questions, please join with me in thanking both Andrew and Dana.